so on this one, the easy thing to do, and many before you have done it also, was to think that what they're telling you is this. They're saying that this is the sequence. Okay, this is not the sequence at all. This is not what they're telling you. They're telling you this is the formula, right? We worked on creating formulas. This is the formula for the nth term. So when you see it in that perspective, then it helps you to get unstuck from seeing that these are the individual terms. They're not, right? So what would C3 be? If this is the formula for the nth term, then this is what you do to get C3, right? So C3 is not 7 over 3. It's this whole thing up till 7 over 3, right? So it's 7 plus 7 over 2 plus 7 over 3. And remember, in web work, you can put in expressions, right? So you don't have to do any simplification. You can just go 7 plus 7 over 2 plus 7 over 3. Let it be your calculator for you. So we got it. Okay, any questions on that one? So I think maybe that was, yeah.
Is there any way to write Cn without having, the ellipsis and the two terms, and just write it in terms of like?
Oh, that's a good question. I don't know off the top of my head. Yeah, I don't know. I'd have to think about it. But it wouldn't be simple. It wouldn't be something easy, but it's possible. It's possible that there's something that would get you that. I think this is basically the sequence of partial sums for the series 7 over n. So there's John. All right. Any other questions before we keep talking about sequences? Yes, sir.
So we C2 be 7 plus 7 over 2.
Right. Yeah. So this is the formula for the nth term. So if it's n equals 2, then you're going to do this sum until you get 7 over 2. The light bulbs aren't going off. So, I guess it's easier when longer. So what would be C of 6? C of 6 would mean this is the formula for when n equals 6. You plug 6 in for n. So you're going to have 7 plus 7 over 2 plus 7 over 3 plus 4, 5, and you're going to stop when you get to 7 over 6. So that's the 6th term. So the second n equals 2 would be, you would just stop there, because there's where n equals 2. So you would just have that much of it for n equals 2. Okay, other questions? All right, let's continue talking about sequences. So we left off last time with these two common forms, and I want to change to make it so when we get to series, which is the next thing we'll do after sequences, to make it consistent, I want to change the lettering here. So either change your notes or take new notes here. So this 1 over n to the p, we said as long as p is any positive value, this thing will go to 0, right? Even if it's square. So 1 over the square root of n, that's p equals a half. Square root of n still gets large for large n, and n to the 1/10. N to the 1/10 still gets big for large n. And so if the denominator gets big, then the thing goes to 0. So this is going to goes to 0 as n gets large if that exponent is greater than 0. Now, so I just wanted to make it consistent with what we're going to do later. I want to change the notation. I had r before. We want to say p instead. P, okay? So we can have our own little term for this. We'll call this the p sequence. So I'll tell my kids tonight at the dinner table that in class we talked about the P sequence, and I'm sure they'll giggle about that. Everything's about poop and pee these days, right? Okay, so it doesn't change, right? Even in college. Okay. All right. So then So then instead of P to the end, we're gonna do R to the end. Again, this is going to be a geometric sequence. Okay. So we're going to call this geometric sequence. Is where n is the exponent. So now n is the exponent. So for what values of r does this thing go to 0? So for what values of r, when you keep, so every subsequent term in the sequence is just multiplied by another r, right? So r to the first. So what is the sequence? R to the first, r to the second. So when will this thing converge? Okay, so it's when what goes to 0 when you multiply it over and over again? Fractions, right? Fractions. Magnitude less than 1. Magnitude less than 1. Okay, so if you have like 2, that's going to blow up, right? But if you have 0.8, if you keep multiplying, taking 0.8 of the thing you had before, that will get small. Same with negatives. So negative 0.7, that will get small, but negative 2, that will blow up and alternate, right? Blow up and alternate as n gets large. So this is going to, this geometric sequence, we need r to be between -1 and 1, and then you're always taking a fraction of the term you had before, and so then eventually that will get small, that will go to 0. That should make sense. Does that make sense? And we call that the geometric sequence. So we have the P sequence and geometric sequence. And then there's another kind of trivial case. If r is 1, then that sequence is 1. But it's kind of a trivial case. This is really the important case here, the first one. That's the important one. But if r is 1, then you just get the sequence 1, 1, 1, 1, 1, 1, 1, and that goes to 1. Okay, so the name of the game with sequences is, do they converge or not? Is it going to converge to a value, meaning it gets the terms of the sequence keep getting closer and closer to a particular value? Or does it diverge? And we talked about 2 ways something could diverge. It could get really big negative or positive, the terms of the sequence, or the terms of the sequence could oscillate and not really hone in. So the idea of convergence is you're honing in on a particular value. If you don't hone in on a particular value, anything else happens, it's divergent. Okay, it's divergent. So here's some other strategies for analyzing, figuring out, by analyzing we mean figuring out if the terms of the sequence converge or diverge. So we talked about the associated function, right? The associated function. You can take do the limit of the function that's the continuous version of that sequence, right? You can list out terms. Just look at the terms. So we've done some of that. Just list out the first 5, 6 terms and just look at what they're doing. Okay, general algebra, pre-calc knowledge, and then there's some common sense involved in this. So every sequence there's all different kinds of sequences that they would be thrown at you. And we should also add to this list of these general forms, right? General forms above. So we want to know how the general forms work and be on the lookout for those. What? P sequence and geometric sequence. So if the first that's like the first thing to do is to look for, do you have one of these two? Do you have one of these? And then apply what we know about those. If not, can we do some algebra to get it to be one of those forms? Or do we need to list out the first 6 terms and see what we have? So this is just kind of practice because there's no really one. There's lots of different sequences that they can throw at you and ask you, convergent or divergent. So let's do some practice. You've already had a little practice, but now we kind of summarized kind of your toolbox for this. Can I go on to the next screen? So what you want to do here is practice And all of these should really be in braces here. Okay, etc. They should all be in braces. So you know, maybe you don't have to do this on all of them, but at least on some of them, practice writing out the first three terms. So just so that we remember that what we're looking at is a list, right? We're looking at a list of values. That list goes on forever as n just continues to march along. The list goes on forever. So we just want to keep that in mind, that when we look at one of these, we're looking at an infinite list of values. And then we're going to reach into our sequence toolbox that I just showed you and try to figure out convergent or divergent. Okay? And we want to always, you know, justify your answer. State the reason that you're using to make your conclusion. If it's convergent, determine what the terms of the sequence are honing in on, right? What's the limit of the terms of the sequence? Okay, so we'll take 10 or 15 minutes to... Okay, Farah, you're first. Did you get the first one? -4 to the n? Do you think that's convergent or divergent, and why? Okay, and what reason do you cite for that? Okay, good. So she recognized that hopefully you saw this is a geometric sequence, right? This is r to the n. R to the n. And since r equals -4, that's outside of our range for convergence. Okay, did you get? Did you write down the first three terms of it? What are the first three terms?
-4, -16, -64.
Almost. -4, positive, right? And then -64. So clearly you can see by looking at the terms, this is going to be really bad, right? Really bad when we talk about convergence, because it's going to get bigger positive alternating with bigger negative. But we also want to recognize this is a geometric sequence with r equal to -4, divergent.
If we were asked if it diverges to positive or negative infinity, how do you answer that?
No. It's right. It's alternating between the two. Yeah. So you can't answer that question. It's not either. It's neither, because it's alternating and getting large positive and negative. Okay. Where's Braden? Tell me about. Did you get this sine one?
Yes. So I said it converges to sine of 1/3.
Okay. He says that converges to sine of 1/3. Because?
Because the powers are the same, so they're equal, so it's just 1/3.
Good. All right. So we can just put the sign on hold at first, right? Put the sign on hold and just look at the convergence or divergence of the argument. And this, what, goes to, he said, 1/3 as n gets big. Therefore, this thing, so these numbers for large n just get closer and closer and closer to 1/3, so the sequence converges to? He said sine of 1/3. Agree with that? So yeah, sine is an oscillating function, but that's when you just let its input increase. What's the input doing here? The input is getting closer and closer to a particular value, 1/3. So sine's not going to oscillate, right? It's not that in this case the sequence is not going to oscillate. It's going to get closer and closer to sine of 1/3. Okay, very good. Where is Ben? You're up. How about this one? Did you get it? Oh, 1 over square root of n.
I said it's 0.
Okay.
If you look at the square root function, it kind of looks like it's leveling off, but it does go to infinity as x goes to infinity.
So your argument is that square root of n
Or you can say
gets.
it's 1 over n of 1/2 squared is 0.
Okay. Sure. So either way, so you can argue that square root of n will get large as n gets large, therefore this thing will go to 0. Or you can see it as a p sequence, right? P sequence with, we got 1 over n to the 1/2, and 1/2 is greater than 0. So convergent, or converges to 0. Okay, next one. Caitlin, you're up. How about this next one?
Oh, it's divergent because it goes back and forth.
Yeah, so it doesn't, convergent sequence has to hone in. The terms of the sequence have to get closer and closer to one particular value. If it's jumping around like this, it's divergent. Okay, next one. John, you're up.
So I'm assuming it's a square root problem.
The what? Yeah, sorry, yeah. Mhm.
Alright, so I kind of disregarded the square root.
Okay.
And looked at the function on the inside.
Right.
And I saw that the degree in the denominator was higher than the degree in the denominator.
Okay.
So that's going to approach infinity. That value is going to approach infinity. And then just taking the square root of infinitely increasing numbers is just going to be divergent.
Yeah, so looking at degree of numerator greater than degree of the denominator means this thing will get big as n gets big. And likewise, the square root of a bigger and bigger numbers get big as well. So this diverges. That goes to positive infinity, right? So that one goes to positive infinity. Manuel.
Oh yeah, since it's in the square root, would it matter if you first got like square root of n to the 4th, kind of like that, like simplifying it to then find out if it's divergent or convergent, or since it's the same, since they're both under the square root, it wouldn't matter.
Are we back to saying that
Also, n equals 1.
this equals this? It kind of sounded like you were saying that.
It's not like that. Like, I mean, to find out that the power of the degree at the top is higher than that of the bottom, like that, would you have to go through the whole getting the square root of n to the 4th thing, kind of just to find out if they're really.
I'm not following you.
Yeah, never mind.
Ask me after the class. All right. Next one. Where is Logan? You're up. Did you get n to the -4?
I still haven't watched the last lecture.
Okay.
So I,
But you could do this based on what we talked about at the beginning. Would n to the -4 is the same as what?
The negative 4th is the same as n 1 over n to the 4th.
Okay. Convergent or divergent?
Kind of looks like convergent, right?
Because?
Because as n gets infinitely bigger, it's gonna approach 0.
Yeah, so certainly our denominator is going to get really big. This will go to 0. How else could we argue this one? What is it, Kelly? What's that?
Sorry, the P rule is P greater than 0.
It's a p sequence, and we got 4 is greater than 0, right? 1 over n to the p, as long as p is greater than 0, goes to 0. So yes, that is convergent to 0. Okay, how about this one? Pi to the n over 3 to the n. Where's Garrett? Is Garrett here? Is there still a Garrett in the class? Zachary. This is an old list. Yeah.
Okay, so no matter what position in the sequence, 1, 2, or 3, the exponents are going to be the same in the numerator and the denominator.
Okay.
So you're just going to approach pi over 3.
So you're thinking n to the pi over n cubed. No.
Wouldn't it just be like if you had the second sequence, it would be.
No, so it's different. Yeah, so your n's aren't in the base now. So we got the power n.
So it's going to diverge.
Yeah, Corey.
I was going to say it's going to diverge because pi is larger than 3.
Okay.
So whenever you square pi by a larger or the same amount, I guess when you have pi to the same exponent as 3, it's going to be continually longer or like larger, I guess, than 3. If that made any sense at all?
Exponential growth.
Exponential. There you go. Using my words.
Yeah, but both the numerator and the denominator are exponential growth. So you're talking about that
But one is exponentially growing faster
okay.
Because it's a bigger base.
because it's a bigger base.
Anyone have a different? Yeah.
I rewrote it as pi thirds to the n,
Okay.
which is like p to the n, and pi thirds is greater than 1. So it diverges.
Right. So you recognize this is a geometric sequence.
Nice.
Geometric sequence.
Learn something new every day.
Your argument wasn't incorrect though. Yeah. So your argument was good. But so we do want to recognize these p sequences and these geometric sequences. So geometric sequence, and the r value is greater than 1. So divergent. Pi over 3, since it's greater than 1, when you keep multiplying it by itself, right? So the next term is always multiplying by a number greater than 1. You keep multiplying by a number a little bit greater than 1, that's going to get big, right? That's going to get big. That's going to diverge. So divergent. Last one. So what is 3 to the n plus 1? Where's Vincent? Not here? Where is... Kelly just went. How about there's Vincent again? Elizabeth. Where's she? There, over there. How did this last one go? Any progress on that? Okay, and why? How come? Okay, so usually a bigger denominator would help something to converge, not diverge. So what does 3 to the n plus 1 mean? So we really got to know our rules of exponents with all these sequences in series. What does 3 to the... How could you say what 3 to the n plus 1 is? Yeah?
Like 3 to the n times 3.
Right, so before we had in the denominator we had n 3's multiplied together. Right? 3 to the n means you keep multiplying 3 together n times. So now what do we have? We have multiplying to 3 together one more time than before. So couldn't we rewrite it 1/3 times what? Pi over 3 to the n. Do you see it? So it's really just 1/3 of the previous, every term has 1/3 of the previous sequence's terms. Converge or diverge? Still pi over 3 to the n. This diverges. Take 1/3 of it. That's not going to help. I mean, that's still 1/3 of really big numbers still gets really big. Okay? So divergent, same thing. It's a divergent geometric sequence. Okay, questions on any of these? Questions on any of these? Okay, so we got to talk about factorials. Factorials. So in mathematics, this is not 4, right? 4. Okay, this is 4 factorial. 4 factorial, which means start with 4 and keep multiplying down until you get to 1 and then you stop. So you start with a number that's the factorial, so start with 4, and then you're going to keep multiplying down through the whole numbers down till you get to 1. So 4 factorial is 24. 4 times 3 times 2 times 1. Okay, as a rule, 0 factorial is not 0, it's 1. So we just have to have that as a fact. Okay, it's a fact that we just have to remember. 0 factorial is not 0. 0 factorial is 1. Okay, so find 6 factorial. Write what it means and find the value. Write out what it means explicitly, find the value. Yeah, write out what it means and then find the actual value. No, you don't need a calculator.
We already know 4 times 3 times 2 times 20 is 24. So just multiply that.
Okay, Miranda, where's Miranda? She came in, right? Over there. How'd you do? 6 factorial. So what does it mean? So if we write out, what does it mean? And did you find the value? Yes, it's be 720. So it'll be 30. It'll be 5 times. So really, we could use. How can we use 4 factorial to help us? Notice that in 6 factorial.
It was 30 times.
Yeah. So notice that within 6 factorial, 4 factorial is a factor of it. And so you could use that to help you with the arithmetic. But notice that for every factorial less than 6 factorial is a factor of 6 factorial, right? 5 factorial is a factor of it. 3 factorial, 4 factorial, 2 factorial, etc. So that's important to remember. That within any given factorial, you have a factor of all the factorials before it. Yeah.
How is 0 factorial?
We'll talk about it later.
So you're terminating definition.
Yeah, it's a definition, and then so and it,
There's also a 0 factorial in the 6 factorial.
it's true. Yeah, but it's
What's 0 factorial?
yeah. So that's not that will take too long to talk about. That's not an quick, easy answer. Okay, so then, what about this? 28 factorial divided by 25 factorial. So given what I just said, that can help you greatly to not be spending 5 minutes on this, right? So how can what I just said help us to simplify and make this not so hard anymore? Tell me.
What's that?
Yeah.
The multiples.
Uh-huh. That's all math. That's all math. You just think about it. But what did you? Trevor, tell me.
I think I got it. So I'm just trying to picture if you had them all lined out.
Yeah.
Like do 28 on top and then 25 on bottom.
Okay.
Then you could cross them off, so you could just do 28 times 27 times 26.
What are you crossing off?
All the 25s, like all the. And then
Yeah, it's 28 times.
Does that make sense?
Right, exactly. So within 28 factorial, do you see that we have what?
7 what factorial?
25 factorial is part of 28 factorial, right? It's a factor of it. 28 times 27 times 26 times 25 factorial is 28 factorial, right?
So we're crossing off the 25 factorial.
Right. So then that simplifies to 1, and you're left with 28 times 27 times 26. So that's not so bad. So it's not so tedious anymore, right? Still, we need a calculator to do that quickly. Okay, so here's a sequence using factorials. So maybe before we do that, let's practice one more. Can you write out what n plus 3 factorial would equal? So before we get to the sequence, can you write out what n plus 3 factorial would equal? Can you write it out? Try that. Gerardo, did you get it?
Yeah.
Tell me.
Would be n plus 3
Good.
times n plus 2 times n plus
And would we stop there at n plus 1?
1
Times
go until 1.
What would be 1 less than that? So n could be a number like 500, right? So we keep going down. What's 1 less than that? N. And then what's 1 less than that? Minus 1. And minus 2. And then we're going to just keep going until we get to 1. So 3 times 2 times 1. So does that make sense? That we're just following the rule about factorial, that you start with the number that you're given, and then you keep multiplying by the number 1 less than the one before until you get to 1. So 1 less than n plus 3 is n plus 2. Then n plus 1. Then 1 less than n plus 1 is n. 1 less than that is n minus 1. Then n minus 2, etc. down to 3 times 2 times 1. So, write the first 3 terms of this sequence. So when n equals 1, you get the first term of the sequence. And then when n equals 2, you get the second term. When n equals 3, you get the third term. So write out the first 3 terms. We'll just do that first. Let's get the first 3 terms first. Okay, Boris. Is Boris here? No? Not here? Jesus. Where's Jesus? Okay, how would you get the first term? How would you get A1? What would you do? Yeah, so what would you get? What would we get? It's 1 factorial, right? Over when n is 1. 3 factorial is equals 1/3?
Yeah.
Nope. What is 3 factorial? 6, right? 1/6. Okay. How about A2? Manuel, did you get A2? Did you get do the second term of the sequence?
No, I didn't.
Okay, let's do it together. Go. So when n is 2, what do you get?
Second one.
A2. Yep, the second term of the sequence.
6 divided by.
Where'd the 6 come from? So it's
Sorry. Can't do that.
it may be 6. I want to know where it came from.
Oh. 2 times 2 minus 1.
Which is
Factorial.
okay.
3 factorial.
3 factorial on the top. Good.
Was 5 over 5 factorial.
And what does that equal?
Divided by 1.
Right. So, and we could also do what? We could see this as 5 times 4 times 3 factorial, right? So this would be 1 over 20. Question?
Could you simplify 2n minus 1?
Yeah, that's what we're about to do. That's what we're about to do. We're just practicing seeing this as where we get the terms. But yes, we're going to do that next. So in A3,
So that
no, that's great. No, that's a good question. That's right. That's what we want to do. So A3 is? How'd you get that? 5 factorial over 7 factorial, which is 1 over 7 times 6, right? So just looking at the terms, what do we suspect? Convergent or divergent? 2? 0. It seems like it would be convergence to 0, but let's prove it. So we want to do what Corey said and expand the numerator and the denominator and simplify this. So how can we rewrite a sub n? The denominator would be what? 2n plus 1 times 2n times
2n minus 1 factorial.
right, 2n minus 1, 2n minus 2, but that's just 2n minus 1 factorial, right? So the rest of the terms of 2n plus 1 would be the same as the terms of 2n minus 1 factorial. So they go, and we get the sequence 1 over 4n squared plus 2n. So that's equivalent. So 1 over 4n squared plus 2n is equivalent to this original form of the sequence that I gave you. And that'll give you the same terms, what was it? 1/6, 1/20th, 1/42nd. And clearly this goes to 0 because it's something like a p sequence with p equal to 2, right? It's like a p sequence with p equals 2. Is that a stretch or a hand? So goes to 0 as n gets big. Okay, so we're done with sequences. We'll start series on Friday. Series is when we take these terms of a sequence, the list, and we add them up. Start adding them together.